Okay, let's get started. Today we're going to be doing 16, 16.8, and maybe 16.9. So 16.8 is so-called spherical coordinates. Okay, so this is, again, another coordinate system that you're going to put on R3. Right. Last time we had cylindrical coordinates, which turned out to be just polar coordinates combined with Cartesian coordinates. Right. So you take polar coordinates in the xy plane and then Cartesian coordinates in the z direction. Spherical coordinates is maybe like a more honest generalization of polar coordinates. So it's sort of like polar coordinates for R3. But not in the lame way that was done last time. Right. So basically like polar coordinates for R3. Okay. So we do the following. We describe each point in space, each point in R3. Is described by three coordinates, rho, theta, and phi. This is rho, theta, and phi. In case you don't know your Greek alphabet, rho, theta, and phi. Right. Where rho is the distance of the point to the origin, theta is basically the same as in polar coordinates, and I'll make that clearer with the picture, same as in polar coordinates. And phi is the angle made with the positive z-axis. Angle made with the positive z-axis. Okay, so here's the picture. This is x, this is y, and this is z. Then, and you have some point here. Then the length of the vector here is rho. So this length is rho. This angle here is phi. Right? You see that? The angle with the positive z-axis. Right? You go there, down here. That's your phi. Okay. So like if phi is pi over 2, then you're in the xy plane. Right? If phi is pi, then you're pointing straight downwards. Okay. And then. Right, I'm going to drop a perpendicular down to the plane here. Okay, so drop perpendicular down this way, and then the angle from the x-axis, to the to this line is your theta. So if this is r, if we call this thing r, then this point would be, r theta. Using this point in polar coordinates on the xy plane would be r theta. Right? So we're basically using the theta from polar coordinates. Okay. Okay. Everyone see that? Right. So rho is this, theta is this, and phi is this. Okay. Or if you like phi, you could also think of phi as this. Right? It's the same thing. It's because you've got the two parallel lines. You've got parallel lines here, and so right, this angle and this angle are the same thing. So that both of those guys are phi. But it's probably easy to think of it like this. Okay. So Okay, right. So this thing here is the projection of rho theta phi on the xy plane. This guy here is rho theta phi. There are two ways of writing phi. Sometimes you write phi like this. So if you see both, either of those things is called phi. Okay. Okay. So notice, make a remark. Notice that the cosine of phi cosine of phi is the z is the z coordinate, right? Cosine of phi is the z coordinate over rho. Right. So that gives us that z is rho cosine phi. And that sine phi is r over rho. It's r over rho. And so that gives us that r is rho sine phi. Right. And so our Cartesian coordinates, if we want to go to the go from the spherical to the Cartesian coordinates, Cartesian coordinates of rho theta phi are cosine theta, right? So r cosine theta r sine theta times and then z. This is r cosine theta, r sine theta, right? The x and y coordinates we get by using, by thinking of them as polar. R cosine theta, r sine theta, and we have the z here. Any questions? So some objects, as usual, like some objects are more easily expressed. Using spherical coordinates. If I'm talking about a solid ball of radius a, right? Solid ball of radius a. You could describe that in a couple ways, but maybe this is easy. So I'm going to let my theta range from 0 to 2 pi. I'm going to let my phi range from 0 to pi. And I'm going to let my rho range from 0 to 0 to a. Any questions about the solid ball? Make sense? Right. Your points, you're gonna let the theta range over the full circle, right? Your phis are gonna range like this, like all the way down to the bottom, and you're gonna have something like this going all the way down to the bottom, all the way around, right? And then the range of the distance to the origin will be from 0 to a. Right? You could, I suppose, you could do this in a different way. You could say like let phi range from 0 to 2 pi, right? If phi ranged from 0 to 2 pi, but then if you went all the way around, you'd cover it twice, right? So you get two solid spheres. You get two solid spheres on top of each other, right? So you'd have to make this one from 0 to pi to compensate for that. Okay, clear enough. Okay. Suppose we have a hollow ball, right? Hollow ball. Right. So you could have something like this, right? So rho goes between one radius to another radius, right? With the analog of the annulus. That's pretty straightforward. You could have something like this. I'll write it down and you tell me what it is. So theta goes from 0 to 2 pi again. Phi goes from 0 to some omega. And rho goes from 0 to a. So what's that? Suppose like omega is some small number. Like less than pi over 2, say. Yeah, hold on.
Does it kind of look like an ice cream cone?
Exactly, looks like an ice cream cone, right? You've taken the solid ball, right? You've taken your solid ball, and you've cut out of it, right? You've let things only go up to angle omega, right? So you cut out of it something like this, where the maximum angle you can have from the z-axis is omega. Right? So this, is this is something that we described earlier, but as you see, describing it with respect to spherical coordinates is really trivial. Okay. Okay. So the game again will be that we'll take our integrals and then we'll change them into spherical integrals. And I'm not going to work out the scaling factor, but if you want, right, you know how to do it. But you have, I just erased it, but p sine p sine p cosine theta, as in rho sine p sine theta, rho cosine theta. Right, this is your map, right? And then you'd have the derivative of this with respect to rho, with respect to phi, with respect to theta, with respect to phi, different of this guy rho with respect to theta, phi, etc., and you have this matrix, and you take the determinant of the matrix. So the scaling factor, in this case, you can work it out. Turns out to be rho squared sine phi. Which is the determinant of the matrix of the derivative of this map. Okay. So for example, we can do things like calculate the volume of a ball. Right, the volume of the ball is a triple integral. You're integrating 1 dv over the ball. Right? But instead of integrating, instead of trying to do it with Cartesian coordinates, we'll just do it with spherical coordinates. Can you do it? Take 20 seconds. take 20 seconds and write down what the integral should be to get the volume of the ball. Hey, Coldwell, do you want my jacket? Use my jacket. No, nobody. I wouldn't use it except it's mine. It's so shabby looking. My wife periodically tries to get rid of this jacket, or to buy other jackets, but somehow I always lose them. Not intentionally. I'm not sure where they are. It's Joe. I know it sounds suspicious, but I like those jackets. I just don't know where they are. I left one at my sister's house, and she apparently gave it away to like a homeless person or something. That's a good jacket. Okay. Yes. So. What's the integral? Right. We need. So, what? First off, what are we going to integrate here? Peter? The scaling factor. Right. The one is still a one. Right. No matter what you do with it, it's still going to be one. So the only thing we have is a one here, and then we have the scaling factor, rho squared sine phi, and then whatever order you choose, right? I don't know. It's sort of up to you. You know, d phi, d beta, d. Let's say d rho, d phi, d phi. Right. Phi goes from 0 to pi, beta goes from 0 to 2 pi, and rho goes from 0 to the radius of the ball. Right. So the radius. Do you want to do this integral? Not particularly. It's not exciting, right? But you know what's going to happen. 4/3 pi a cubed will pop out of it in the end, right? And you see how that's going to happen, right? You've got the rho cubed over 3 will give you the a cubed over 3, right? And then you've got the 2 pi there, and then you've got the 2 there. Okay. Another example. Okay. So another example from 38 in the text. You have some function f of x, y, z being 1 plus x squared plus y squared plus c squared to the negative 2. And you want to integrate over the solid. You get the solid that is above the cone. Z equals root x squared plus y squared, and below the sphere, x squared plus y squared, excuse me, plus c squared equals 3. So this is exactly that ice cream cone that we were dealing with before. Right? You have some sphere, right? And then you have a right cone. You have a right cone going out of it. Cone going out of it. So, yeah, take a minute and set up the integral. Okay, turn to somebody next to you and say what your integral is, even if you haven't evaluated it.
So there's the 2 pi. And then let's try something since it's the cone.
And 0 to 2 pi.
Since it's a cone, couldn't we just do like for what's it called for row? Couldn't we do like 0 to whatever
Sine inverse of
and
radius divided by.
I think, this is my guess, I don't know. So, what we want to do is strip this like only a bit.
right?
And I think so that cone is just like the x equals y line.
I think
If so, let's have it by name. So that would illustrate that angle from zero. Yeah, you want to restrict
right.
to the angle that that cone makes, which I think is half.
Okay, so let's write it down. Who would like to say what we're integrating over? First, we need to describe the object, right? So what's the object? What can you say about it?
Theta goes from 0 to 2 pi.
Right, theta goes from 0 to 2 pi. Okay, somebody else want to say something about it? Right, that's easy. I'm laughing because of course that's easy. I'm sure you can say more. Yeah, Paul.
The angle of phi goes from pi to the angle of whatever.
The angle of phi. The angle of phi goes from pi
to the angle between the cone and the z-axis, which would be sine inverse of r divided by.
Oh, wait a second. So phi is the
It's the upper.
phi is
of that.
the angle to the z-axis, right?
Yeah.
The angle to the z-axis, right? So we only want this part, right?
So it would be the lower bound.
So it goes from 0 to
What's that?
right. When it's here, it's 0, right?
Okay, yeah.
When
And
it's
it
here,
would
it's
go
0.
from 0 to sine or whatever phi is, which would be, if you have to put in terms of other like variables, it would be like sine inverse of r divided by rho.
Wait. Let's think about
Sine of
let's
phi equals r over rho, right?
sine of phi.
Yeah.
Okay, so right. So
In terms of
it's simpler than this. It's simpler than this. So just look at it, right? Here we have, if we say project this thing onto the, if we look at this thing on the xy plane, say xz plane, excuse me, xz plane. So y is 0, say, and y equals 0. Right, this thing, it's a cone, right? Right. So z is equal to the absolute value of x. Right. So it's going to look like this. Right. So what's this angle?
45 degrees.
45 degrees. That's it.
Okay.
Yeah. So so phi goes from right. So the cone, right, is this thing spun around the z-axis, right? So the angle throughout is going to be pi over 4. So just pi over 4. Okay. And then the row is going to be from where to where? Up here.
0 to 3.
0 to root 3.
Root 3.
0. Okay. So then we're going to integrate this thing over that object, right? So we have, we're integrating this function over there, and so we're going to integrate f at f at x y z. Right, and then rho squared, the scaling factor, and then d rho d theta d phi z. Right, and so right, these guys are going to range over what we just said. You know, phi goes from 0 to pi over 4. Theta goes from 0 to 2 pi, and rho goes from 0 to 3. Okay. So, right. So, if you wanted, you could work this out, right? You could say, okay, you know, f evaluated, right? We're gonna take f at, you know, we substitute in rho sine phi cosine theta for x, you know, rho sine phi cosine theta for y, and rho cosine phi for z, right? And that would, right? So we get blah blah blah, right? 1 over 1 plus rho sine phi cosine theta squared plus rho sine phi sine theta squared plus rho cosine phi squared. Everything to the negative, everything squared on the bottom. Right? Oops. And we have d rho d rho d theta d phi. And you got the rho squared sine. Right? But yes, Alana?
Sorry, does it matter if you switch the d theta and d phi, or like and switch the bounds?
Nope, nope. You could do it in
It's
whatever.
not like
you-
easier either way.
It may well be. So I mean, we can look at it and see if one is easier. If it is easier, we can switch it. Yeah, but it doesn't matter. Yeah. This is basically integrating over a parallelepiped, right? Integrating over a parallelepiped, you know, you can just change the bounds. It's very simple to change the bounds. Right. Okay. So you could one way you can figure out the function is to plug everything in, right? Or maybe easier, you recognize that x squared plus y squared plus z squared is what? X squared plus y squared plus z squared is the distance to the origin squared, right? Which is in the spherical system, it is going to be rho squared, right? So we didn't really need to write all this. Really, it's blah blah. 1 plus rho squared d rho d phi, right? And then all the appropriate things here. Zero, 0 pi 4, 0 2 pi, 0 3. Okay. So then you would integrate it. You would integrate it from there. I guess maybe the only hard thing is the integration. How would you integrate this first integral with the d against d rho? Does anyone have an idea? This is more like a Calc 2 question, Calc 2 test question. Does this look familiar to you? Partial fractions, yes, exactly. So you use method of partial fractions. Use so-called partial fraction decomposition. Right. get that, if you work it out, you get that this thing equals 1 over 1 plus rho squared minus 1 over 1 plus rho squared quantity squared. Okay. And then there are things you can do to integrate these guys. Yeah, I mean there may be a few of these sorts of things in the homework, but yeah, I'm not gonna test you on them. Right, that's prior knowledge. Okay. Okay. Clear how to do this. Okay. Right. Just like before, right? You evaluate your function at the appropriate point, and then introduce the scaling factor, right? In order to integrate over this simplified region. Yeah, Peter.
Will we ever be converting from cylindrical coordinates to spherical coordinates?
I guess you could. You could. I don't think you will, but there's no reason why you shouldn't. Yeah, I think it'd be pretty messy. So I don't think you do in the text, but theoretically, there's nothing against that. Last sort of example. Somebody gives you an integral in Cartesian coordinates. So x squared plus y squared plus z squared to 1/2 e to the negative x squared plus y squared plus z squared dx dy dz over the hollow ball x squared plus y squared plus z squared ranges between 1 and 4. So you have a ball of radius 2 containing a ball of radius 1. The ball of radius 1 is pulled out, and you integrate this function over that region. Okay. And so you're asked to do this using Cartesian coordinates, but of course you instead switch it to spherical coordinates. Okay. So take a minute and write down the corresponding integral. this, and then you create a corresponding scaling factor. Right. It's not hard, but it's not hard, but it won't be pleasant. Okay, so Lily, how about you? What do you get?
So the integral is from 0 to 2 pi, 0 to pi, and 1 to 2.
Mm-hmm. Right. And so you're going d rho, d phi, d theta. Right, and you need a scaling factor. Right, and then I need. Mm-hmm.
Since x squared plus y squared plus z squared is just rho.
Yeah.
So
Right. So that's it. Sorry.
That's it. That helps you cool.
Yeah.
Just, yeah.
Thanks. Sorry. Let's do it. Yes, Alana.
Can you show really quickly why x squared plus y squared plus z squared equals rho squared?
Yeah, sure. I mean, in fact, I can sort of describe it, right? What's
Yeah.
x squared plus y squared plus z squared, right? If you're here, and here's your point x squared plus yz, x squared plus y squared plus z squared is the distance to the origin squared, right? That's the magnitude of x, y, z is, x squared plus y squared plus z squared to the half.
Okay.
Right, right. That's this length here, right? But rho is, what was rho? Rho is the distance to the origin. That's this, right? That's this. So that's right. That's this. So rho is literally this thing.
Mm-hmm. Okay.
It's exactly that thing. Okay. So I'm not sure what to do. Like, we could start the next section, but there's only 7 minutes left. I think we'll just stop here for today. Maybe that's good. I'll just hand back some homeworks and we'll stop here. Next section will. No, so I can talk a little bit. So what we've been doing are what are called change of variables, right? We have one set of, we have the x, y, z variables, and we're changing to some other set of variables, right? And so far we've seen 3 examples of that: polar coordinates for double integrals, cylindrical and spherical coordinates for triple integrals. It turns out that these are just 3 examples of an infinity of possibilities. Okay, you can do change of variables. You can set up your own change of variables as you like. However and try your own ways of making the integral simpler. Okay, as long as you follow the rules and introduce the proper scaling factors. Okay, and then so what we're doing next time is giving the general theorem and then showing some examples of where we don't have any specific coordinate systems, but we make up our own coordinate systems to simplify things, and that's that. Okay.